Okay, in the next situation, we're given that an object is accelerating downward at 9.5 meters per second squared. For there's no reason to have changed the mass. We'll call it a 300-gram object. Maybe it's the same object under different circumstances. Now, that's pretty close to 9.8 meters per second squared. And it's accelerating downward at this rate. So we easily calculate that the net force is 2.85 newtons. Okay, of course we are careful to express our mass in kilograms so that we multiply by the acceleration. We do get kilogram meters per second squared, so we can call it newtons. Okay, now we know if it's accelerating downward at 9.5 meters per second that there's a gravitational force on it. Okay, and we also know that since something that's in free fall, anything has a gravitational force of a gravitational force which would, if no other forces were acting on it, accelerate it downward at 9.8 meters per second squared. We know that the gravitational force is then 0.3 kilograms times 9.8 meters per second squared. Now again, this is downward because gravity accelerates things at this rate downward, and because we used a downward acceleration to get our net force is also downward. So we have to be careful about what's upward and downward. Okay? So our net force is our gravitational force plus our total non-gravitational force. There might be various forces acting on this thing that aren't gravitational. We do expect there to be some air resistance. Okay? So now we can plug these quantities into this formula. That's not a formula, it's an equation that we've written, actually. We can plug these quantities into our equation and then solve for the non-gravitational force. Probably better to solve for the non-gravitational force first and then plug in, but either way, you're going to find that the total non-gravitational force is what? This minus this, which is 2.85 newtons downward, and then minus 2.94 newtons downward. That represents the net force, which is downward, minus the gravitational force, which is also downward. And when we work this out, we get a negative force, negative 0.09 newtons downward. Now that's the same as an upward 0.09 newton force. So you see that we've got to be very careful about what's upward and what's downward. And of course, it can be very helpful to express everything in vector notation. So if we expressed this in vector notation, we'd have, let me do that in a different color. .85 newtons times negative j, if we use a standard coordinate system, equals uh, 2.94 newtons here, which is downward, so it's 2.94 newtons times negative j, and then it's going to be minus the gravitational acceleration, which is going to be 2.85 newtons times negative j. Okay, if you work this out, you find, and it's not, okay, I was about to write this equation, and I started to do that, then I wrote the next equation. So, I'm just going to, how am I going to fix that? Let's see. This is our F non-gravitational, and it's going to be pretty sloppy, but I don't want to have to stop and restart the camera and splice two videos together. So I'm going to just slop it down here. This is your total, which is your F grav minus your F net. Okay, and we just again used the J vector with a vertical horizontal coordinate system to indicate this.